Jai Hind to all. My name is Divya Sharma. My today's video lecture is on antenna parameters. First is beam width, directivity and resolution, beam area. So these are the fundamental parameters of antenna. Radiation pattern already discussed in the previous lecture. So today we will discuss this beam width, directivity and resolution and beam area. And these are other parameters of antenna: radiation intensity, gain, effective aperture area, antenna temperature and antenna impedance. So these parameters we will discuss in the next video lecture. So now today we'll start with this beam width. The angular separation between two half power point is known as half power beam width. So half power beam width, how we can calculate? As you all know, P is equal to E square upon eta. So already you all know this formula. Power is equal to electric field intensity square upon efficiency. Now here, let it be P is directly proportional to E square. P is equal to E square. Now here, let P is equal to half. If P is equal to half, put here value P is equal to half is equal to E square. E is equal to, means if you are calculating for half power beam width, so P is equal to half, E square is equal to half. So we can calculate here E is equal to 1 upon under root 2, and that is equal to 0.414. So, sorry, 0. Okay, just wait. 1 upon the root 2 is 0.707. Okay. Now here, this is the point where we are getting half power beam width. So this is the maximum radiation when we are sending signal from transmitter to receiver. So we will receive signal in form of radiation. So this is the maximum radiation, and here we are calculating here. This is E is equal to 0.707. So these are the points where we are calculating, means angular separation between these two points, that is known as half power beam width. Now these are your side lobes. Okay. Now there are three types of patterns are there: isotropic pattern, directional pattern, omnidirectional pattern. So first is isotropic, where we have radiation, means we have equal radiation in all direction, that is known as isotropic antenna. Let it be this is your test antenna. And you have uniform radiation in all the directions. And here is some intended antenna. So if we have radiation, if we have equal in all direction, then you can say that is known as isotropic antenna. Now second is directional antenna. Directional antenna is an antenna which radiates or receives electromagnetic waves more effectively in some direction. And third is omnidirectional pattern. Now omnidirectional pattern is a special type of pattern where we have in 2D pattern, where we have figure of 8 is the pattern of omnidirectional antenna. So this is the field pattern. So already we have done that E is equal to what? Sorry, E is equal to 0.707. If you want to calculate it in dB, that is equal to what? That is 10 log 10 in bracket this E. So we can calculate that is equal to minus E is equal to what? 1 upon 2. So if it is in denominator, so we will get output in form of negative, that is equal to minus 3 dB. Okay. Now here you can see the field pattern in linear scale. Now here this is the angular distance in between these 2 points, that is known as half power beam width. Now here you can see the radiation. This is the maximum one. Here is 0.5. So we can calculate according to that. This is 0.707. Now here this is power pattern. If you want to calculate power pattern in linear scale, so this is the radiation pattern Now here you can see this is the maximum radiation. Now here already we have done how we can calculate half power beamwidth. So these are the points, means these are the points where we are where these points are touching on this major loop. These are your points 0.707. Here this is 0.707. So this is your half power beamwidth, angular distance between these 2 points, that is known as half power beamwidth. Now first null beamwidth, it means what? Where there is no radiation. So there is no radiation, so angular distance in between these two, means when we are drawing angle at this point, so angular distance in between these two null points, that is known as first null beamwidth. So this is major loop, and except this major loop, other lobes are known as side lobes, and or you can say other lobes are minor lobes. So, and back lobe, already we have done in the previous lecture that back lobe is the 180 degree of the, let it be, this is your intended lobe. So back lobe is the 180 degree of this intended lobe. Now here directivity and resolution. The resolution of an antenna may be defined as equal to half the beam width between first null, means F and B divided by 2. This is known as your resolution of an antenna. Let it be an antenna whose pattern F and BW is 2 degree, has a resolution of 1 degree, and accordingly it should be able to distinguish between transmitters on 2 adjacent satellites in the geostationary orbit separated by 1 degree. When the antenna beam is maximum aligned with one satellite, first null coincide with the adjacent satellite. Now half power beamwidth, if you want to calculate half the beamwidth between first null, is approximately equal to half power beamwidth, or you can represent it as, this is the beam area. So ohm A is represented as beam area, that is equal to first null beamwidth upon 2. You have to represent it in form of theta and phi. So first null beamwidth divided by 2 in form of theta, and first null beamwidth divided by 2, that is in form of phi. So then number is means if you are taking n number of radio satellites or n number of point sources of radiation distributed uniformly over the sky, then antenna can resolve, that is approximately resolution is represented by n. N is equal to 4 pi upon beam area, and beam area is represented by ohm A, and that is equal to first null beam width upon 2 in form of theta, and first null beam width upon 2 in form of phi. Now here you can see resolution is equal to what? Resolution is equal to directivity, that is equal to 4 pi upon beam area. Now ideally number of point sources, let it be, here are n number, so directivity is equal to n, and number of points, or you can say number of point sources in the sky where you will get the ideal conditions of uniform source distribution. Now what do you mean by field region? So when you are sending signal from transmitter to receiver, so your signal in form of radiation, the space surrounding an antenna is usually subdivided into 3 regions. So first is reactive near field, second is radiating near field, that is also known as Fresnel zone, and the third one is far field region, that is known as Fraunhofer zone. Now first is reactive near field, so region surrounding the antenna where in the reactive field predominates, that is r less than 0.62 under root d cube upon lambda. And the second is Fresnel zone, where region between reactive near field and far field, that is known as Fresnel zone. You can see this structure, this is the structure, this is the antenna. Now here this is the maximum dimension of the antenna. This is your antenna, and its maximum dimension of this antenna is representing by d. So this is maximum dimension of antenna. Now here, this is the region, this is the reactive near field region, and its radius is R1, and the other region of radius R2, that is known as radiating near field, or you can say Fresnel region. And the after that means if your space is up to infinity, so that is far field or Fraunhofer region. So these are three regions, or you can say these are subdivision of space. So R1 is equal to what? R1 is equal to 0.62 under root d cube upon lambda, and R2 is equal to 2d square upon lambda. Now here, this is the inner circle of radius R1 is the antenna zone. So this is the antenna zone where you have reactive near field region of radius R1. And now here, second is Fresnel zone, region between reactive near field and far field region, that is known as Fresnel zone. And you can say for directivity, if your directivity is greater than lambda, so you can see this, your R varies from 2d square upon lambda to 0.62 under root d cube upon lambda, means your region, this is your region, it varies in between this and this. Now, third is far field region, region where angular field distribution is essentially independent of the distance from antenna, that is your Fraunhofer zone. So, our region is greater than 2d square upon lambda. So, this is the field region, how we can differentiate reactive near field. Second is radiating near field, that is known as Fresnel zone, and the third one is far field region, that is Fraunhofer zone. Now third is how we can measure the plane angle. So we can measure the plane angle in form of radian. If you want to measure the angle, solid angle or plane angle, so we can measure in form of radian and steradian. So the measure of plane angle is radian and measure of solid angle is steradian. So 1 radian is defined as the plane angle with its vertex at the center of a circle of radius r intended by an arc whose length is r. Now if you want to measure the solid angle, then solid angle is you can measure it in form of steradian. And 1 steradian is defined as the solid angle with its vertex at the center of the sphere of radius r that is subtended by a spherical surface area equal to the square of the each side of the length r. Now here, area of the sphere is equal to what? If you have radius r and area of sphere you want to find out, that is equal to 4 pi r square. Now if you want to measure it in steradian, so you can write down here 4 pi steradian, or you can write down 4 pi r square upon r square, because if you want to change it in steradian, you have to divide 4 pi r square divided by r square. So you will get here 4 pi steradian in a closed sphere. Now 1 steradian is solid angle of the sphere divided by 4 pi. So 1 radian square, so you can calculate it, 1 radian square is 180 degree by pi square in degree square. So you can calculate in form of degree square. Now here, if you want to find out 4 pi steradian, that is equal to what? 1 steradian is equal to 3282.8064. So you can multiply it by pi by 4 pi. So you will get here this value. This is for the solid angle in a sphere. Now here, let it be you have a sphere or you have a solid space. You can see here, this is, you can find out if you want to find out plane angle, you want to measure the plane angle, so you can easily find out. Let it be you have a circle and this is your radius r, this is also radius r, so you can find out the angle in between these two radius, and that is represented by 1 radian. But if you have a solid angle, then solid angle you can measure solid angle in form of steradian. Let it be you are taking some part, this is your solid angle, you are taking some area of this solid sphere and you are measuring this area from the center of the sphere. So this is represented as r. Now here, if you want to find out the area of this area, so area is equal to pi square. If you have radius is r, so area is equal to r square, and if you want to measure the angle of this solid angle, that is 1 steradian. Now, so this area of this solid sphere, that is equivalent to, let it be, this is a rectangle of area is equal to r square. So this area and this area are equal to each other. So this is the how we can measure, this is the structure how we can measure steradian for a solid angle. Now, spherical coordinate and solid angle. So these solid angle is measured in form of steradian. Now, already we were discussed in the previous lectures that how we can write down the coordinates of Cartesian coordinates, cylindrical coordinate, and spherical coordinate. Now we have to find out, we have to consider here spherical coordinates, because we are finding the angular distance between 2 points. So for angular distance, so we have to consider here spherical coordinates. Now here, if you want to write down spherical coordinate, this is your x-axis, this is y-axis, this is z-axis. So this is, and for spherical coordinates, you should know r, theta, phi. So these are the coordinates of spherical coordinates. Now write down these coordinates in this structure. Here, this is your radius, or you can if this is your area of sphere, so write down here, let it be, this is your r, this is your phi angle, and if you are considering some angle of this phi, you can represent it as d phi, and this is the radius of this area. Now here theta, if you want to measure angle theta, so this is angle theta. As you already know how to write down coordinates of spherical, r, theta and phi. If you are considering here small part of angle of phi, so represent it in differential phi, so d phi. Now here, if you are taking some angle of theta, so represent it as d theta. Now considering here in this sphere, in this part of sphere, you have to consider this strip has area 2 pi r sine theta r d theta. Now here, when you are drawing this angle, this area, so you have to consider this part of this strip. So if you want to consider this part, so area dA is equal to r square sine theta d theta d phi. And here, this is what? This is your d ohm, means solid angle. Because if you have r square sine theta d phi, so divided by r square, then you will get the solid angle. This is your dA. So if you want to, if you will divide dA by r square, then you will get here d ohm. Okay, that is equal to what? Solid angle. It is represented as sine theta d theta and d phi. So this is the way how you can calculate solid angle. Solid angle is this one. Now, let it be, you are considering this is your equivalent solid angle. This is your beam, means this is your actual pattern of the beam area, ohm A. Here, this is your major beam, these are your side lobes. Now you are considering here major lobe. Here you have to represent equivalent solid angle, ohm A. This is your equivalent solid angle. Now actual pattern of the beam area, this is your actual pattern of the beam area, that is represented as ohm A. Now here half power beam width, as already we have discussed that how to find out half power beam width. Now here in this figure, this is the antenna power pattern and its equivalent solid angle and beam area, and beam area is represented by ohm A. Now in polar two-dimensional coordinates, an incremental area dA on the surface of the sphere, that is the product of the length r d theta in theta direction and r sine theta d phi in phi direction. So your dA is equal to what? R d theta and r sine theta d phi. Now here you will get here r square d ohm. If you want to find out here dA, so you can calculate it like this. Now this is d ohm is solid angle expressed in steradian, or you can say square degree, and d ohm is also subtended by area dA. Now area of the strip of width r d theta extended around the sphere at a constant angle theta is given by 2 pi r sine theta r d theta. if you will integrate it with theta values, so you can integrate it and find out the area of the sphere. Area of the sphere is 2 pi r square. Your angle is theta is equal to theta values are 0 to pi and sine theta d theta. So you can integrate it and you can find out area of sphere while you are considering the theta values are 0 to pi. So that is equal to what? 2 pi r square. So this is the area of the sphere. Now beam area. Beam area, or you can say beam solid angle, that is represented as ohm A of an antenna, that is given by the integral of the normalized power pattern of our sphere 4 pi steradian. Now how to find out beam area? Beam area is what? In integration, you have to write down normalized power in form of theta and phi and sine theta d theta and d phi. So here you have to take the values for theta and phi. So theta values are 0 to pi and phi values are 0 to 2 pi. So already in the figure, according to that, the previous figure, we can write down the values theta and phi. So you can integrate it and you can find out the beam solid angle, that is equal to what? In integration, normalized power theta phi and d ohm. So ohm, d ohm. So you can find out beam area in units steradian. Here where d ohm is equal to what? Sine theta, d theta and d phi. So write down here, this is equal to d ohm. So ohm A is the solid angle through which all the power radiated by the antenna would stream if P means power in form of theta and phi maintain its maximum value over ohm A. Otherwise it will be 0. So power radiated is equal to what? Power radiated is P in bracket theta comma phi and ohm A. So this is the power radiated. Now beam area of the antenna is calculated, is approximately in terms of angles by the half power points of the main lobe. And half power points of the main lobe, how you can write down? Beam area is equal to ohm A, or you can write down theta half power and phi half power. That its unit is also, beam area units are steradian. So this is the way how you can find out beam area in form of normalized power or with parameters theta and phi and d ohm. Now radiation power density. So radiation power density, power associated with an electromagnetic wave instantaneous Poynting vector, that is W is equal to E cross H. So W is instantaneous Poynting vector, its units are Weber per meter square. E is instantaneous electric field intensity, its units are volt per meter, and H represents magnetic field intensity, its units are ampere per meter. So Poynting vector is the power density, and you have to calculate here total power that crossing a closed surface, and you can calculate here power, that is closed integral W dot ds. So ds you can find out in form of unit vector, or you can write down in form of unit vector n vector dA. So P is instantaneous total power, watt unit, and n is the unit vector normal to the surface, and dA is the infinitesimal area of the closed surface, its units are meter square. Now average power radiated by the antenna, that is equal to what? P radiation is equal to P average closed integral WRAD dot ds. So you can put the value here, ds, that is unit vector, and dA. Now here W average is equal to E cross H. If you want to take real part of E and H, that is equal to half of E and H. So here write down the real part of E and H and take half common outside this closed integral dot ds. So this is your average power radiated by the antenna. Now total power radiated by the isotropic antenna. Already we have discussed that isotropic antenna, because we are considering here ideal condition, and for ideal condition we are considering here isotropic antenna. Now for isotropic antenna, P radiated is equal to closed integration W naught ds. So write down here the value of W naught and ds. So ds already we discussed that you have to write down here in form of unit vector, r unit vector, r square sine theta d phi. So this is the surface, means ds, differential surface of the sphere, and already you know how to write down the differential surface of the sphere is r square sine theta d theta d phi, and your unit vector is ar. Now here w naught, so write down here w naught is also in form of unit vector, so ar unit vector w naught in bracket r. Now power density is equal to what? So w naught is equal to unit vector of r, means ar unit vector w naught. Now you all know w naught is equal to what? P radian upon 4 pi r square. So you can write down here, this is the uniformly distributed of the surface over the surface of the sphere of radius r. So you should know w naught is equal to what? Unit vector of r, p radian upon 4 pi r square. When you are putting this value, means here you can find out p radian is equal to 4 pi r square w naught. So from this derivation you can find out w naught is equal to p radian upon 4 pi r square. Okay, so this is the formula for this power radiation. Thank you. Next parameter we will discuss in the next lecture.